Did you know that intermolecular forces are holding it all together? No, really, they are. IMFs, as I endearingly call them, are holding everything together. By the end of this video, you should be able to identify what IMF or IMF, intermolecular force, is present based upon a chemical structure or atoms present, and what IMFs even are to begin with. For today's lesson, first we'll be talking about intermolecular forces. What the heck are they? And then we'll be discussing the types there are: ion-dipole, hydrogen bonding, dipole-dipole, or dip-dip, as I like to say, and London dispersion. Then we will practice identifying a few of these IMFs on some chemical structures. IMFs literally stands for intermolecular forces. I want you to think of intermolecular as interstate. If you were going to say, oh, drive on the interstate, you would be driving between states, hence the name interstate. The whole point is that it connects two states together. For example, when my husband and I drove cross country to get here to Virginia, we took the interstate highways all the way across the country from Arizona to Virginia. So interstate, just as it would imply between states, intermolecular would imply between molecules. So this is a force that is occurring between molecules, between two separate molecules. These forces are dependent upon whether those molecules have polar or nonpolar characteristics. If you're not sure how to identify if a molecule has polar or nonpolar characteristics, please see my previous video, which I have linked on the little card that's showing up in the corner up there, so that you can familiarize yourself with that content as well. There are four types that we'll be discussing of IMFs specifically. We're going to talk about ion-dipole, hydrogen bonding, dipole-dipole, or dip-dip, and London dispersion. IMFs control physical properties. So physical properties could include boiling point, melting point, the mass, density, whether or not a chemical is a solid, liquid, or gas at room temperature or at another temperature. These are physical properties of a chemical. These IMFs, these intermolecular forces between molecules, is what creates the boiling point or melting point for a different chemical. If it has a really strong IMF, it takes longer to boil. In other words, when you think of strong IMF, you want to think of two molecules that are holding on really tight to each other. They're strong. So you can think of that as like the force between my fingers. They are really holding on tight to each other. So two chemicals that are holding on with a force takes longer to boil if this is a strong force. In other words, it would take a lot of energy added to break this intermolecular force between the two molecules. Energy meaning you could either rip my hands apart, or energy most likely in the form of heat or electricity for chemicals. It would take a lot of energy to separate them from each other. If it has a weak IMF, on the other hand, it'll boil very quickly. This equates to a very weak force. So you can imagine two molecules barely holding on to each other. Notice that with my fingertips, if I'm barely holding on, they separate fairly easy if I'm trying to pull opposite directions. So if we add energy, whether that's in the form of heat or electricity or what have you, these two chemicals have a weaker bond between them. So they're not going to be able to stay together as easily as something with a strong IMF that's holding or clenching to each other a little bit more tightly in that regard. So it would be a lot faster of a boil or evaporation. So flashback now to a previous lesson. If you haven't seen that lesson on polarity, again, please click on the card. It's in the corner. Watch it. You should inform yourself on it. We did a little mini experiment with water and acetone. We put a drop of water and a drop of acetone on a plate, and we said, okay, what's happening? After some time went by, we saw that the acetone drop was gone. It vanished, it evaporated, and the water droplet was still on the plate. The reason for that is because the one that evaporates faster has weaker IMFs. They're not holding onto each other as tightly. The one that takes longer to evaporate is holding on tightly, has a strong IMF or a strong intermolecular force. So if we had more than one water molecule, which we always do, if you're drinking a glass of water, there are literally thousands of water molecules in that single glass of water, and they're all holding on to each other really tightly. So water has a really strong IMF between other molecules of water with itself. And that's why it takes so much longer for it to evaporate or boil in this case. Whereas acetone does not have a very strong IMF. It has a very weak IMF, so it's not holding on to itself very tightly or other molecules of itself. Therefore, it evaporates really quickly. Let's go over our 4 IMF types. The first being ion-dipole. This is the strongest IMF that we have present. This is when we have something that has a salt. Again, a salt is something that has charges on it. So that would be like your ions. If we dissolve ions in water or a polar solvent, water does happen to be polar in this case, so it's a good example, but there are also other polar solvents. If we take a salt, which is composed of ions, positive and negatively charged particles, and we dissolve that in water, we can see then that the water is going to align itself around those charged particles in such a way that the slight positives or slight negatives will be balanced by the full positives and the full negatives. If you look at this picture right here, you can see that NaCl is my full charges. That's my salt. NaCl is table salt, sodium chloride. So together, these two atoms make table salt. Dissolved in water, our little Mickey Mouse heads here, that's H2O. We can see that there's a full negative. The orientation of the water molecules around this full negative is such that the hydrogen, or the slightly positive regions, are pointed towards the full negative region. However, if we look at the sodium, where there's a full positive, the orientation of the water molecules is flipped, and we see that oxygen, or the slightly negative region, is pointed towards the full positive region. This is an example of an ion-dipole IMF. So the attraction between this full positive and this slight negative, and the attraction between this full negative and this slight positive on these different water molecules is the example of an ion dipole. Again, this is in between. So it's this invisible space between these two different atoms. This intermolecular force is occurring between these atoms, not inside the molecule. The second type of IMF is called hydrogen bonding. Hydrogen bonding is the second strongest IMF and always results when we have a partial positive that happens to be a hydrogen atom and a partial negative that happens to be either FO or N. The dipole that occurs between oxygen and hydrogen, or fluorine and hydrogen, or nitrogen and hydrogen, which is an intramolecular force, that's the actual bond inside the molecule, happens to form a very strong dipole. And because of that very strong dipole, what we see is that when we get a bunch of that same chemical together, we get hydrogen bonding, and they create a network, like the picture above my head. There's literally this whole Tetris network of hydrogen bonding occurring, where your water molecules, as an example, because there's hydrogen and oxygen present in water molecules, arrange themselves such that the slightly negative on the oxygen of one molecule will be pointed towards the slight positive of the hydrogen on a different water molecule. Notice that this is a force indicated by dashy lines between two different molecules, hence intermolecular force, between the two different molecules. A way to remember this is hydrogen bonding is how, H for how, often, like often, but like often, does hydrogen bonding happen. So how often, it's always going to be between hydrogen and either fluorine, oxygen, or nitrogen. So just to reiterate, that dashy line is indicating an invisible force between one molecule and another molecule, and that specific force is a hydrogen bond because it's between hydrogen and oxygen. The third type of IMF is dip-dip or dipole-dipole. This is the third strongest, or almost the weakest, if you want to think about it that way, in terms of intermolecular forces. This is when we have partial negatives attract partial positives in a polar molecule. So this is kind of the same as the hydrogen bonding, except we can have different atoms other than O, F, or N attached to the H. In this case, we have Cl attached to H, if you look at my picture over here, for hydrochloric acid. So since this is Cl and not O, F, or N, this can't be hydrogen bonding. Instead, it's dipole-dipole, or dip-dip. Dipole-dipole is going to have the same kind of attraction on two separate molecules as we saw for hydrogen bonding. We're going to have attraction from a slight negative region to a slight positive region on two separate molecules from each other. They're going to orient themselves next to each other in such a way that their slight negatives will be next to their slight positives and vice versa. And finally, we have London dispersion. This is also known as induced dipole or van der Waals. This is a force that happens between fats primarily, or nonpolar molecules. So molecules that already have weak dipoles or that happen to be nonpolar tend to have London dispersion as their intermolecular force. In this case, fats, like your oils and your butters, are made up of a lot of carbons and hydrogens. And if you watched my previous video, you know that carbon-hydrogen bonds are nonpolar bonds. So that nonpolar aspect is already a weaker bond in this case. So weak dipoles. And that creates a weaker intermolecular force. This happens to be the weakest IMF that we have, the weakest intermolecular force, but we can add it up over a large molecule. So I want you to think about Velcro for a second. If you have a very small piece of Velcro and you were to put the two pieces of Velcro on top of each other, this bond is easy to rip apart if you needed to. You could probably separate those two Velcro pieces fairly simply. However, if you took a whole sheet of Velcro and a whole nother sheet of Velcro and you smashed them together, it's actually surprisingly difficult to peel those apart from each other. Likewise, with London dispersion forces, what we see is that, okay, if you have a smaller, shorter carbon-hydrogen fat molecule, or a carbon-hydrogen molecule in general, and it just happens to be shorter, there's not a lot of contact between the two separate molecules. And so you can kind of peel them apart easier. In other words, they can evaporate faster, they tend to go to a liquid form faster, or, so on and so forth. However, if you have really big fats, really big molecules of fat, they're like the huge pieces of Velcro that you've sandwiched together. Even though they are weaker dipoles in each fat, in each longer fat, they now have more connection to each other through that intermolecular force, and that makes it more difficult to peel them apart from each other. So the bigger the fat, or the bigger the molecule of CH bonds, increases that intermolecular force, even though it's still London dispersion and it's still the weakest of the IMFs. You can also think of London dispersion forces as an instantaneous force. So it's almost like two areas containing electrons bump into another area containing electrons, and instantaneously the electrons will shift in such a way that you get a slight negative region and a slight positive region. But then those readjust because, remember, in nonpolar bonds there's an equal sharing of electrons. So it's only an instantaneous change where the electrons will shift but then kind of go back to equilibrium or go back to equal sharing. So they might bump over to unequal sharing for a split second but then bump back over to equal sharing. This is called an instantaneous dipole, and this is what causes London dispersion to occur between those fat molecules, which are primarily made of nonpolar carbon-hydrogen bonds. Due to that induced dipole, or because, hey, the electrons bump over and tend to shift the other electrons, you get this cascading domino effect where the electrons are going to shift and create regions of slight positive and slight negativity in which the whole molecule can align and be like that Velcro stacking that I just talked about. So in summary, we have our 4 IMF types, the strongest being ion-dipole. The next stronger would be hydrogen bonding, or below ion-dipole would be hydrogen bonding. The middle strength would be like your dip-dip, your dipole-dipole, and that would be basically the same as hydrogen bonding, except for something else that doesn't have O, F, or N. And last but not least, we have our weakest, which is London dispersion forces, or van der Waals, or an induced dipole. Let's give it a try. So if we were going to look at these different chemical structures, and we wanted to identify the IMF that would be present for each. Let's try and see what's present and then classify it into one of our 4 types of IMFs. Let's start with acetone. Acetone has a dipole arrow. The reason I know that is because carbon and oxygen have very different electronegativities. That means that oxygen would be slightly negative and carbon would be slightly positive. In this case, our dipole arrow would be pointing towards oxygen, meaning that we have an overall net dipole going up. However, we also have areas of nonpolar bonding. We have similar atoms like carbon-carbon, which is a nonpolar bond, and we have carbon-hydrogens, which we know is always nonpolar bonding. So in this acetone molecule, well, we want to first think, does this fit into ion-dipole if we just had a bunch of these everywhere? No, not really. We don't see any ions. We don't see any full positive or full negative charges anywhere on this molecule. So it can't be the first IMF. How about the second one? The second IMF is hydrogen bonding. Hydrogen bonding requires that there are hydrogens, and either the hydrogen is connected to O, F, or N. In this case, we do have hydrogen, but the hydrogen is not connected to O, F, or N. It's connected to C. Okay, so that doesn't quite work out very well. What if we imagined another acetone molecule right next to it? In this case, since we have an uneven distribution of electrons between carbon and oxygen, we're looking at our third type of IMF, which is our dip-dip. So that's where you have a slight positive and slight negative region, just happens to not be between hydrogen and oxygen, fluorine, or nitrogen. So because it's between carbon and oxygen, we're looking at dip-dip for the IMF of acetone, which is our middle strength, middle grade IMF. Water then. Water has 2 dipole arrows, one pointing towards the oxygen this way and one pointing towards the oxygen that way. We have an overall dipole pointing up between those 2. We see that there is O connected to H. We don't see any full positives or full negatives, so it cannot be ion-dipole. But because we have an O connected to an H, we know it has to be hydrogen bonding, which is our second strongest IMF. So water has actually a pretty strong intermolecular force. Okay? How about the last one? This is butane, like in a butane lighter. Butane is entirely composed of carbons and hydrogens. Because it's only made up of carbons and hydrogens, that means it's nonpolar. Because it's nonpolar, means it has to fall into our van der Waals or London dispersion forces that we talked about last. London dispersion is our weakest force of all the intermolecular forces. So if we're thinking about which chemical would take longest to boil, we want to think about in terms of strength. If butane is our weakest, so it's holding on by the fingertips, it doesn't take a lot for it to boil, for it to evaporate. Acetone, we said, was our third strongest. We said it was dip-dip, so it's holding on just a little bit stronger, but still doesn't take too much to get it to evaporate, which is what we saw in the previous lesson's mini experiment. And then, if we look at water, water was our second strongest IMF with hydrogen bonding, and water does in fact, out of this list, take longest to boil or longer to evaporate. Again, we did witness that in our little mini experiment where the water droplet was still on the plate, but the acetone was long gone. That was due to how strong the water molecules were holding onto themselves versus how strong the acetone molecules were holding onto themselves. That's all I've got for you on this lesson. Stay tuned for an IMF lab, and we're going to test those intermolecular forces and see if what I told you is actually correct. We'll see. Come see me again for that IMF lab in the future, and I hope you love science just a little bit ducking more. See you later.
Have you liked and subscribed yet? Because if you haven't, you should. Really. Please.
Thanks.
No ducks, no glory.